A cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So in this problem, we have a constraint on our problem. It's made to hold 1 liter of oil. So that means this is going to be a secondary equation. We want to find the dimensions that will minimize the cost of the metal. So that is going to be our primary equation. So 1 liter of oil, that's telling us about the volume. Cost of the metal, that's telling us something about the surface area. So we'll read it again. We'll draw a picture. A cylindrical can. So we need a cylinder. Cylinder has a radius and a height. A cylindrical can is to be made to hold 1 liter of oil. So we know 1 liter is equal to the area of the base of a cylinder is a circle, so pi r squared times h is the volume of our cylinder. So no matter what we do with r or h, we need to keep this 1 liter. Now 1 liter isn't a very convenient unit to work with. We would be better off with 1,000 cubic centimeters. Since centimeters are linear distance, so centimeters squared would be area. That's going to be our surface area. It's going to be centimeters squared, and volume will be centimeters cubed. This will be more convenient to work with. So now we need to come up with the surface area formula for the cost of the metal. If we were to take a can opener and dismantle this can, we see that we've got the top and the bottom are both circles with radius r. So you have a surface area of the top and bottom. Top bot is going to be 2 times 2 times pi r squared. Then we've got, when we unravel this, we have a shape like a rectangle where we made this cut here and around the top would be this distance here. So this would be 2 pi r, the circumference, and then this would be h. So the surface area of the side is going to be 2 pi r h. So the total surface area is going to be 2 pi r squared plus 2 pi r h. This is the thing that we want to minimize. So this is our primary equation, which means this is the thing we need to take the derivative of. Right now, it's an equation with 2 independent variables, r and h. We need to use our secondary equation to write this all in terms of just 1 variable. It looks like it would be most convenient to solve for h, so I'm going to come back up here, divide both sides by pi r squared to get h equals 1,000 divided by pi r squared. Now I can substitute h in to my primary equation, and now we have surface area equals 2 pi r squared plus 2 pi r h, and h is 1000, divided by pi r squared. Now we have our equation completely in terms of r, so we can take the derivative of it and find the maxes and mins. Before I do that, I'm going to just do a little bit of algebra in order to make this more conducive to taking derivatives. So let's bring the r squared up top and combine it with the other r's. Let's cancel out some pi's here. Let's simplify one of those with one of those to give us one of these. And multiply the 1000 times the 2. So 2000 r to the negative 1. This is our primary equation. Now might be a good time to talk about the domain of the surface area. What kind of values can r take? Well, look at the picture. R is the radius of our can. What kind of numbers can we use for a radius? Well, it's got to be at least 0. Also notice that it can't be exactly 0 because you had to end up with a 0 in the denominator of this fraction. So r needs to be larger than 0. Would there be any upper limit on what r could be? As r gets larger and larger, this can would become flatter and flatter to keep a total volume of 1 liter. So r can get as large as we want. So it looks like the domain for the surface area is going to be from 0 to infinity. Of course, that's the mathematical domain. The practical domain, might be just 0 to some kind of large number. So now we need SA prime, or if you prefer, which you probably don't, dSA dr, the derivative of surface area with respect to r. So this is going to be 4 pi r minus 2000 r to the negative 2. Our goal is to get some critical values and do our number line, find the maxes and mins. So at this point we can do some factoring, or we could get a common denominator. I like factoring, so I'm going to factor out 4r to the negative 2, which leaves me with pi r cubed minus 500, which is 4 times pi r cubed minus 500 divided by r squared. So on our number line, what do we want? We want whatever makes the top 0 and whatever makes the bottom 0. We know 0 would make the bottom 0. We also know that this stuff over here doesn't matter because it's not in the domain of our problem. What makes the top 0? Setting the top equal to 0, you would get 500 divided by pi under the cube root. So whatever that is. Nobody cares what that actual number value is. Taking a test value a little bit larger than 0, if I use 1 as a test value, we see we've got 4 times a negative number divided by a positive number is a negative number. So we have a decreasing function here. Then if I take a very large number, for example, if I take 500 cubed times pi is very large, minus 500 is positive. You have a 4 times a positive number divided by a positive number gives us a positive number, so we have a positive slope here, telling us we have a local min when our radius is the cube root of 500 over pi. That is, we have a min of the surface area when r is the cube root of 500 over pi. All that's left is to test any endpoints and make sure that this is a min. We don't actually have to do that in this problem because if we look at the graph of the surface area, taking 0 and finding the total surface area at 0, we know that value is going to be larger than the cube root of 500 over pi because of the way our function is decreasing than increasing. So this isn't just a relative min, this is actually an absolute min of the surface area from 0 to infinity. And let's make sure we've answered our question. Cylindrical can holds the oil, find the dimensions. So we have found the radius that will minimize the metal. In order to find the dimensions, we also need the height. So substituting our value for radius back into our height equation, right there, will give us the height of the can as well. If you work it all the way out, you would end up with something like 2 times the cube root of 500 over pi for the height.